Assalamualaikum warahmatullahi wabarakatuh, and a very good day to the chairman, dear professors, dear doctors, and all my fellow researchers. Today I would like to share part of my research with the title An Analysis of Chip Formation in Whole Circularity in Drilling Application and Aircraft Component Perspective. My name is Aisha binti Ahmad and I'm a part-time master research student in mechanical engineering from University of Tenusin, Malaysia. My research aims to investigate the drilling application process and its impact on the hole quality. Maintaining acceptable hole quality is crucial for minimizing the risk of fracture initiation within the airframe structure. Fractures can compromise the structural integrity of the aircraft, leading to the potential safety hazard. Therefore, it is imperative to understand the factors influencing chip formation and hole security during the drilling process, and it also involves studying various parameters such as cutting speed, feed rate, and tool geometries. By analyzing these factors, we aim to identify the effects on chip formation as well as the resulting hole security. Understanding the chip formation mechanism can provide insights into the material removing process and its impact on hole quality. My research used the ISO 2X6 standard, which distinguishes between hole basis widths and shaft basis widths, with the hole basis width having 4 preferred hole tolerance H11, H9, H8, and H7. My focus lies in investigating the factors influencing hole circularity, specifically in the context of chip formation and hole circularity in aluminum 6061 alloy. Achieving a high-quality hole with minimal dimensional variation is of paramount importance, as it not only optimizes productivity but also reduces manufacturing costs and time. By understanding the key factors impacting hole quality in aluminum 6061 alloys such as cutting parameters, tool geometry, and metal properties. One of the challenges in achieving optimal hole quality is the requirement for human labor to monitor the machine status regularly. This monitoring process demands a significant amount of time and energy, which can lead to inefficiencies and potential errors. Therefore, my research aims to explore automation and monitoring techniques that can alleviate the burden on human operators and reduce the need for continuous manual intervention. Despite the significant hole quality in the manufacturing industry, there remains a shortage of studies specifically addressing hole quality in aluminum 6061 alloy from the perspective of chip formation and hole security, as aluminum 6061 is widely used in metal in aerospace, automotive, and other industries due to its favorable properties. Hence, conducting comprehensive research on chip formation and hole security in aluminum 6061 alloy will bridge this gap in knowledge and contribute to a better understanding of the machining characteristics and challenges associated with this material. My research focused on conducting drilling operations on aluminum 6061 aircraft materials and exploring the influence of feed rate on hole security and chip formation, as aluminum 6061 is commonly used material in the aerospace industry due to its mechanical properties. By carefully controlling the feed rate during drilling, we aim to analyze its impact on the security of the resulting holes and the formation of chips. This will provide insight into the optimal feed rate for achieving high-quality holes in aluminum 6061 material, ensuring the structural integrity of aircraft components. Additionally, our research involved studying the effectiveness of machining operation in chemical software on hole security during operation times. This software enables precise control of machine operation by examining the machine operation parameters, tool path, and cutting strategies implemented through Kimco software. We aim to evaluate the influence of whole security and will help to optimizing the machining process and identifying any potential improvement or adjustment required in the software setting to enhance the quality in aluminum 6061 aircraft material. The scope of the study encompassed conducting drilling tests on the aluminum alloy 6061T6 with a workpiece thickness of 20 mm, a diameter of the HSS tool ribbon is 10 mm diameter, and the Mazak 3-axis machine as the drilling process, and the software used is Kimco MDC Max. To measure the whole security of using coordinate measuring machine CMM, and for the chip thickness we're going to use digital pointed micrometer. Hole security is a crucial aspect in the evaluation of drill holes, as it quantifies the deviation of a hole from a perfect circle. Geometric tolerance in 2 dimensions allows for the assessment of this deviation, considering the measured circle within a specified tolerance zone formed by 2 concentric circles. The security error, which is the difference between maximum and minimum diameters of the measured circle, is used to determine the extent of security deviation. By calculating the security error as Rmax minus Rmin, the magnitude of the deviation from a perfect circle can be quantified. Understanding and analyzing the security error provide valuable insight into the quality and precision of drill holes, aiding in the optimization of drilling process and ensuring adherence to required dimensional specification. In the field of metal cutting, chip formation refers to the process of generating chip structures in the formation zone during machining operation, as mentioned by Ashtakov in 1997. Chips are formed as a result of the shearing action between the workpiece and the cutting edge. Understanding chip formation is crucial as it plays a significant role in determining the success of machining operation. The type and the characteristic of the chips created during the machining process vary depending on factors such as cutting parameters, tool geometry, and material properties. By studying and analyzing the different types of chips that are typically formed, researchers can gain insight into the machining process, optimize cutting conditions, and improve chip evacuation mechanism. This knowledge contributes to the enhancement of machining efficiency, surface quality, and tool life, ultimately leading to improved productivity and cost effectiveness in manufacturing process. In the context of drilling operation, various types of chip formation can occur which exhibit distinct characteristics and influencing the overall drilling process. We have stable and unstable chips formation. The stable chip formation will divide into 3. There is short tubular chips, spiral tubular chips, and spiral chips. And these 3 were consistent in terms of shapes. On the metallurgy, we are using 5 workpieces of aluminum 6061T6, 10 drill bits of HSS, 1 desktop from Dell. The measuring data collection and monitoring software is Kimco MDC Max. With the vertical center machine is Mazak Nexus. And to measure the whole security, we are using coordinating measuring machine CMM, and for the chip thickness measurement, we will use Mitoyo digital pointed micrometer IP65. And these are the equipments that are being used. And this is the experimental setup. For the result and analysis of the whole security result, It indicates that circularity error of the drill holes increased as the feed rate was increased. At the low feed rate of 0.1 mm per ref, the highest circularity error observed was 0.06 mm, while at high feed rate of 0.36 mm per ref, the highest circularity achieved was 0.085. This trend aligns with the previous research, suggesting that the increase in circularity may be attributed to the rise in cutting forces. As the feed rate increased, the deflection and vibration of the workpiece intensified, leading to accelerated penetration and enlarged circularity defects. It is worth noting that obtained data for hole circularity exhibit instability and inconsistency, with the highest circularity value found in hole 29, possibly due to tool wear. Hole 28 had the lowest feed rate, and in terms of feed rate, hole 23 exhibit the highest value, while hole 18 had the lowest value. This observation highlights the influence of both circularity and feed rate on the quality and stability of drill holes, with the highest feed rate recorded as 0.36 mm per ref. The deflection of the beam towards in a particular direction when force is applied to it is known as beam deflection. The beam can be bent or move away from its original position. This distance at each point along the member is the representation of the deflection. And the chip formation, these are the chip formation results for holes 1 to 15 entity was gathered and recorded. For the chip thickness result analysis, it reveals that the chip thickness is significantly influenced by the feed rate, showing a non-linear relationship. As the feed rate increased, the chip thickness also increased, indicating a positive correlation. However, it is noted that highest cutting speeds, the chip thickness decreased, suggesting a more complex interplay between feed rate, cutting speed, and chip thickness. The non-linear nature of the relationship highlights the need for further research to fully comprehend the underlying mechanism. This finding have implications for optimizing cutting parameters in metalworking and machining process, emphasizing the importance of considering the feed rate and cutting speed to control and optimize chip thickness. By understanding and manipulating chip thickness, manufacturers can enhance machining efficiency, surface quality, and tool life. The observation that chip thickness decreased at high cutting speed aligns with the previous research, with further supporting the need for continued investigation and analysis in this area. On the relationship between circularity and chip formation, drill 9 operated with a feed rate of 0.32 mm per ref exhibit the lowest hole circularity compared to the other drills in the experimental setup. This attributes to the production of small and segmented chips during drilling. The presence of small chips indicates excellent circularity error, as these chips help prevent tool wear and prolong tool life. Additionally, the segmented chips, which break into conical helical shapes before assuming long pitch form, are advantageous for chips discharge and disposal. The segmentation occurs due to the lack of ductility in the material, leading to strain from the drill hole's wall. On the other hand, drill 5 and drill 10 produce corkscrew and tangle chip shapes, resulting in high average circularity. The presence of such uneven chip shapes adversely affects the hole quality, highlighting the importance of chip shape in determining the overall hole's circularity. And lastly, on the correlation of OEE performance and circularity, during the investigation of drill 6, it was observed that the change in shift during the production process had an impact on its performance. The overall equipment efficiency OEE formula, which takes into account the good count, ideal time, and planned production time, was used to assess the performance. The issue primarily stemmed from the planned production time on the ground floor, where the changes in shift affected the OEE. This could result in height misalignment or the need for minor modification, potentially leading to the decreased precision or slower operating speeds. It is crucial to maintain the efficiency of drill 6 as its peak to ensure optimal performance. In terms of average circularity data for different feed rate, the best performance was achieved with drill 7 and feed rate of 0.26 mm per F. This drill demonstrated excellent machine performance as evidenced by the low average circularity error. The efficient operation of the machine has the potential to impact the quality of the workpiece. Additionally, drill 9 exhibits high OEE performance, indicating excellent performance in terms of ability, quality, and overall performance. The conclusion of the research is the study reveals several important findings regarding hole security, chip thickness, machine performance, and data analysis in the manufacturing process of aircraft component. It is observed that as the feed rate increased from 1 mm per F to 0.36 mm per F, the circularity of the hole also increased due to higher cutting force. However, inconsistent hole circularity is observed mainly caused by the hanging workpiece during drilling, leading to vibration and degradation of hole quality. Chip thickness is found to decrease with higher feed rate, reaching a maximum of 0.706 mm at 0.36 mm per F, while drill 1 exhibit the minimum chip thickness of 0.22 mm. The increase in chip thickness is also attributed to rubbing in improper cutting, especially as the number of holes drilled increase. The performance of the machine as recorded by the Kimco and BC Max plays a crucial role in determining product quality. A feed rate of 0.26 mm per F achieves high machine performance and low security, indicating a favorable operation condition. Conversely, drill 6 with a feed rate of 0.23 mm per F demonstrate the poorest machine performance and relatively high average security of 0.09 mm. By analyzing drill behavior, including speed, power consumption, and performance punctuation, valuable insight can be gained to optimize the manufacturing process of aircraft components. Monitoring individual drill performance enables the identification of areas for improvement and ensure consistent, high-quality production standard, ultimately enhancing efficiency and reliability. Implementing this research finding in aircraft component manufacturing can significantly contribute to the advancement in productivity and product quality. By optimizing cutting parameters, minimizing vibration and workpiece hanging, and monitoring machine performance, manufacturers can achieve high level of efficiency and reliability, leading to improved productivity and consistent product quality. With this, I thank you.